Hello everyone! In this video we will continue to examine topic 5.1 electric fields, and in particular we will examine electric fields in conductors. Alright, so up to this point we have studied or considered the idea of electric field outside individual point charges. Okay, so in practice, this means individual protons or electrons or sort of tiny, conceptually small balls of charge. But a lot of conductors and a lot of things that can be charged are extended in space. A chunk of pipe or really any sort of macroscopic object with a random shape. So what happens if you add a big chunk of negative charge, so negative Q, to a solid conductor, like a piece of metal with some arbitrary shape? In particular, what is the electric field like inside the conductor? Now, the very surprising answer is that the electric field is zero throughout the inside of the conductor. Okay? I'm going to do my best to sort of fully explain why that is at a qualitative level. Proving it quantitatively is quite challenging, but we can give a pretty satisfying qualitative explanation. It's worth noting, though, that this is super counterintuitive, and I really want to impress upon you how counterintuitive it is. Remember, we said, or we drew sort of the electric field for both bare positive and negative charges, and sort of you would think that a whole collection of negative charges could not possibly lead to an electric field of zero inside the conductor. Like, why isn't it that electric field lines aren't sort of coming into these negative charges at different points from inside the conductor, as well as coming into them as they are from outside the conductor, right? How is it possible that within this space, and I'll sort of try to highlight it right here, okay, within that space, the electric field is zero? Well, to consider this, remember that charges inside the conductor, and in particular if it's metal, we're talking about electrons, can move. Okay, they can move. That's the key ingredient. And not only can they move, if the electric field were not zero, they would move. And that's super key. Okay, so if the electric field were not zero, they would move. Why would they move? They would move because they feel a force. If the electric field at any point is non-zero, so this is our electric field, and that's sort of placed on a charge anywhere at all, that charge, if it can move, will. We've sort of been considering forces in what's called electrostatics, or arrangements of charge that aren't moving. But if the electrons and the charge carriers can move in an electric field, they do. And in fact, the key to this explanation is that the electrons will move, and they will move very quickly. And in fact, they will move very quickly right up to the point that they exactly cancel out the electric field that they would be responding to. So imagine there was some sort of electric field in here. The electrons will very quickly move such as to cancel it out completely, right? So other charges, not just the Q net here, not just the extra charge that you've added, will move around until the electric field inside the conductor, not outside, but inside the conductor, is zero. So let's flesh this out a little bit. All right, consider a conductor with a whole bunch of free charges. These are the electrons shown here. Obviously, there are many more of them than that. And assume that these electrons here are the sort of internal electrons. So what we're imagining is that the electrons on the outside of the conductor are applying an external electric field to this chunk of the conductor, which is imagined to be sort of inside that space. And these electrons are free to move, okay? They can move it however they want. Now, assume that in that little chunk of the conductor, that external electric field is applied. So we get a E this way, right? That's our external electric field caused by the electrons on the outside of the conductor. Also, I should emphasize that. So what happens in practice if you add a negative Q net is that the electrons distribute themselves evenly on that outside of the conductor. They can't disappear, right? But they distribute themselves all along the outside, okay? And that kind of makes sense. They sort of push away from each other and layer themselves on this outside. All right, so this electric field is applied. And then the electrons themselves, those free electrons, the ones that are free to move, respond to that electric field. Remember that if an electric field is this way, then the force it will produce on a negative charge is opposite the direction that electric field. So these electrons immediately start moving in the other direction. Okay. Now what happens? Well, those electrons now sort of pile up over on the left. They pile up over here. And they produce their own electric field. So these were free charges. They were not producing a net electric field before, but now they are, because they're all piled up on one side. They all sort of pile up on this side. That applies an electric field from those little charges, shown in green, that wasn't there before. So we still have the external electric field. That's produced by the outside charges, those extra ones. And now we have another electric field, that green E, that is produced by the fact that these free charges moved. Now, when do they stop moving? Well, they stop moving when their own field, the field that they collectively produce, those free charges collectively produce, exactly cancels out with the external field produced by that extra charge. So E external plus E of the electrons ends up being 0. That's when they stop moving. And they do this no matter what. And the net result is that anywhere on the inside of this conductor, anywhere the electrons are free to move, okay, and move away from where they are, that electric field is 0. And that is a non-obvious result, okay, non-obvious result. Where is that excess charge then? It's evenly spread on the outside of the conductor, as far away from itself as it can be. You might think that some of it would spread out sort of on the inside of the conductor. But as it turns out, that doesn't happen. Why? Because if there's a little negative charge right here inside the conductor, it will be feeling a non-zero electric field. And as a result, it will move to the outside, okay? So even though it would sort of, if you think about all these electrons trying to get away from each other, it would be better for all of them if some of the electrons sort of took it on the chin and sort of hung out in the middle. None of the individual electrons will do that, because if they did that, then free charges would move in this mechanism so as to cancel it out. All right, so again, where is the excess charge? Negative Q. As we said, it's evenly spread on the outside of the conductor, and if it wasn't, the electric field would not be 0 somewhere inside the conductor. And a consequence of that is that all the electric field on the outside of the conductor, okay, which is not 0, is perpendicular to the surface. So the electric field comes in and touches the conductor perpendicularly to the surface. And that happens because as these electrons and negative charges sort of spread out evenly, okay, they all sort of contribute a little bit to the left and a little bit to the right. And if they're spread out completely evenly, then that little bit to the left and the little bit to the right cancel out, leaving the electric field coming out of the surface perfectly perpendicular. So even if you had a funky shape of a conductor like this, the electric field that goes into that surface will end up being perpendicular. To emphasize this, you couldn't have, for example, if I zoom in here, electric field that entered the conductor like this. Okay, all the electric field lines, if you applied an external electric field, would seem to sort of sprout in and sort of intercept that potato-looking space at a right angle. They would have to, because otherwise the charge would not be evenly spread on the outside of the conductor. Okay. okay? And if there was, let's say it all sort of piled up over here, okay? So you have a whole bunch of charge over here and it weren't evenly spread, then right next to that charge, you would see some electric field on the inside of the conductor. And so the charges right there would move, okay? So same kind of argument as in the previous page. The electric field would cause those charges on the edges of the conductor to move if it were not perpendicular. All right, and our last application of this idea, and this is also not obvious, but it is true and convenient, is that a charged spherical conductor, so think like a ball of metal, either solid or hollow, will produce the exact same electric field outside the conductor as a point charge placed at the center. So just like with mass, where we can treat planets as if they're sort of a point mass with a total mass right at the center of the planet, we can do the same thing with charge. If you take a total negative Q net, okay, and apply it to a conductor, then outside what the radius of the conductor is, that electric field produced by that conductor will look identical to if you took that same amount of charge and put it at a point charge right in the center of the conductor, okay? So if you spread out that charge in a sphere, this electric field, the purple electric field shown, outside the radius of that conductor is identical to what it would be if you had a point charge there. And what that means is that we can use this formula, which is the, strictly speaking, only true for a point charge.